Okay, today we're going to talk about Chapter 5, which is Alternatives to Experimentation, Correlational, and Quasi-Experimental Designs. Let's start with talking about what a quasi-experiment is. It seems like a real experiment because, but you're not manipulating antecedent conditions. Let me give you an example. You could examine the publication records of men and women, okay, and it seems like an experiment because the independent variables is gender, men versus women. But you don't randomly assign people to the male or female condition. Fate does. And so therefore you can't, it's not a real experiment, it's a quasi-experiment at best. How do they differ? Well, you can, as the experiment they give here, the incidence of Alzheimer's disease in patients using ibuprofen, they've tried to tie a lot of different risk factors to Alzheimer's. For a while, they thought using deodorant was a factor in Alzheimer's, and then they realized it was just a matter of social class, that wealthier people were earlier adopters of deodorant, and they just lived long enough to get Alzheimer's disease. So it's tough to establish causal relationships from quasi-experiments. And as I said, in experiments, researchers randomly assign subjects to the antecedent conditions. So this proposed experiment, assigning people to the ibuprofen or aspirin use and then checking their incidence of Alzheimer's, good luck getting compliance in a study like that. I took a medical decision-making class in graduate school. I can give you updated numbers for these things, but only 26% of doctors and nurses working in ICUs even wash their hands between patients. Now, it's supposed to be 100% of doctors and nurses. This is intensive care units, for heaven's sakes, and they don't follow proper hand hygiene procedures. They don't wash their hands between patients. And this is in 2015. 1/4 of them are actually washing their hands. When you actually look at patient compliance, you find that 50% of people with high blood pressure, which is hypertension, are what's called medically adherent for their first year, which means that they take the dosages they're supposed to take when they're supposed to take them. And they also find that about half of the people stop taking hypertension medicine after a year because they feel fine, and so they don't want to take the medicine anymore. So, so that study is a little ridiculous. Or optimistic, maybe that's a better word to use. When should we use quasi-experiments? Well, when you cannot, or for ethical reasons, should not manipulate antecedent conditions. So again, things like alcoholism or gender or handedness, right-handed, left-handed, those are all quasi-experimental studies. Okay, let's start talking about correlations now. How are correlations measured? Well, Pearson's R. That's basically how we do it, and we can determine how strong of a correlation it is by a couple different things. Linearity means that the relationship can be plotted on a straight line, that it's a linear relationship. Okay, curvilinear relationships really aren't detected by Pearson's R, and so although we can see the correlation, we get a low correlation if we use Pearson's R on curvilinear relationships, because Pearson's R is designed to measure a linear or straight line, not a curvilinear or curved relationship. Sign refers to whether it's positive or negative. So positive correlations show a direct relationship. So as one thing goes up, the other thing goes up. So an example would be height and weight. That is a direct or positive correlation. Generally, as height goes up, weight goes up. Negative correlations are inverse relationships. So as one thing goes up, the other thing goes down, and vice versa. As one thing goes down, the other thing goes up. So a good example of this would be immunization rates in cases of measles. So when immunization rates are high, then cases of measles are low. When immunization rates are low, then cases of measles are high. So please immunize your kids. Magnitude is the strength of the relationship. So -1 represents a perfect inverse correlation, and +1 represents a perfect direct correlation. So what if you get a number like 1.62? Would you be like, wow, that is an incredibly strong positive correlation? No, it's just wrong because it can't be. You can't have a positive correlation greater than 1 or a negative correlation greater than -1. Okay. And then the sign is just indicative of whether it's inverse or direct. And so, like, for example, a -0.54 correlation is a stronger correlation than a +0.32. Okay, so you're looking at the absolute value when you're considering magnitude or the strength of the correlation. And the probability is the likelihood that getting that correlation is due to chance. So again, you may have a linear trend, but it's not significant just because it exists. Okay. What does a scatter plot show? Well, scatter plots are great. They're two-dimensional representations of our data. They're nice because you can see the spread of your scores and you can see the line of best fit, or what we call the regression line. And so you can tell a lot of information quickly. One of the problems that we run into with correlation is what's called range truncation, which means it's an artificial restriction of the range of scores. Let me give you an example. The ACT, which a lot of people take to get into college, it shows a low positive correlation with the ACT score and your college GPA. And so it actually shows a positive 0.3 correlation, which is pretty low. Now, the lowest you can get on an ACT is an 8, and the highest you can get is a 36. I've read online that people can get a 1 ACT. That's not correct. You actually get a minimum of 2 points per section, and so the lowest you can get is an 8. Now, if schools let in all ACT scores, there'd be a much stronger correlation between ACTs and college GPAs. The problem is that schools let in a truncated range of ACTs. So for example, an extreme example would be Harvard. Harvard University lets in people basically between 34 and 36 on the ACT. And so, of course, it's not very predictive of how well they're going to do in college, because everyone is basically at the 99th percentile. Even Truman, if you look at Truman, the average ACT for the incoming class is a 27, which puts it right at the 85th percentile. So you're already dealing with the smartest kids, the upper 15%. But even if you look at the range of scores at Truman, you're looking at probably about between a 22 ACT on the low side and a 31 ACT on the high side. That's not the lowest or the highest possible. It's just where most students fall. But that's still a truncated range. And so you end up with a lower ability to predict or get a positive correlation with the ACT because of this. Okay, outliers are extreme scores. And so you can remove them, clean up your data, which is a lot more often like prettying up your data to make your statistics look better. But generally, any scores that are more than 3 standard deviations out of whack are fair game for elimination because you can kind of write those off. The coefficient of determination, or R squared, says how much variability can be explained by a particular predictor variable. So, for example, go back to the ACT, 9% of the variability in college GPA can be explained by the ACT. That's not much. And so that would argue that, that the ACT is not very predictive of your college GPA, of your academic ability. As one more comment about this too, squaring makes everything positive. And so even if you have an inverse or negative correlation, your coefficient of determination is going to come out positive. Correlation does not imply causation, and we can talk about the reasons why. Because of those three reasons, let's talk about them in more depth. Causal direction means that if you have two variables, A could cause B just as readily as B could cause A. So their example is good. You could think about this in terms of depression and alcoholism too. Does depression cause people to drink more, or does alcoholism make people more depressed? We don't know, and so the causal direction is an issue. A second factor is bidirectional causation. Again, depression and alcoholism. So people tend to go into a downward spiral. The more they drink, the more depressed they become. The more depressed they become, the more they drink, and on and on and on. And so that does not necessarily end well. Either when people hit bottom, many times experience a moment of clarity and then stop. And that's a wonderful outcome. The third variable problem is that there could be some third thing which is accounting for the relationship in the first place. So that works for my example too. Family conflict could be causing depression, it could be causing alcoholism, and I think a better example though is there's a relationship between ice cream consumption and the number of people who die from drowning. And you could say, well, that's causal, that there's something in ice cream that causes people to drown. It just drags into the bottom of the pool, and maybe we should stop selling ice cream. But it's pretty easy to see that there's a third variable, which is seasonality. People eat more ice cream during the summer, people swim more during the summer. And so that's what's causing there to be a positive correlation, a direct correlation. Again, the more ice cream that's sold, the more people drown. So watch when you eat ice cream. Researchers use this multiple correlation when you want to know if there's a relationship between three or more variables. So for example, you have a criterion variable, which you label as Y, and this could be something like lifespan, and then predictor variables, which you label as X, and that could be something that predicts lifespan, like gender, women live longer than men, smoking, non-smokers live longer, and education. Generally, the more education you have, the longer you live. You could use or compute a partial correlation when you want to hold one variable constant. So in our previous example, our gender and smoking correlated with each other. It's complex, but maybe. Gender and education, again, maybe. Women have more college degrees than men, and so there does seem to be a correlation there. Researchers use multiple regression to predict one score based on others. So this would allow us to predict a specific lifespan given a number of predictor variables. You can do this. You can go to, there are sites on the internet that do this. There's one called realage.com, and that's endorsed by Oprah, and so it must be good. Or the Harvard Centenary Study, which looks at people who've lived to 100, has questions at livingto100.com. And both of these sites will give you an approximate age that you're likely to live to. Real Age tells you what your actual age is right now based upon your different lifestyle characteristics. Or you could just throw in the towel and go to deathclock.com, where you just put in your gender and your birthday, and it tells you your approximate checkout date, actually down to the minute, I believe. Let's talk about causal modeling, which is based on correlation, which is absolutely hilarious to put into a basic experimental design class, because this is graduate level stats and beyond. I mentioned when I was in graduate school, I took a causal modeling class my third or fourth year, and our test problems were problems that the professor couldn't answer. And so how far we got on them compared to him determined our grade. So this isn't really appropriate for a introductory class, but it's understandable. So let's talk about a path analysis. What this allows you to see are the relative loadings, or what are called beta weights, for each predictor variable. So you can use statistics and computers, because you can't do this stuff by hand, to make correlations seem causal, meaning that you can make predictions. So for example, if you stopped smoking, if you're a smoker and you stop smoking, how many more years does that give you? Path analysis allows you to calculate that. This is very tough, though, because stopping smoking is something that will kill you earlier. Here's a good question. Is it worth it to exercise, specifically to run? I'm a runner. What the data shows is that exercising, specifically running, adds years to your life, but not as many years as the time you spend running. And so therefore it's essentially a zero-sum game. You can use that time, the hour a week you were going to run in your 30s, for something else, because it's not like you get that hour back later. I mean, you do, because you live longer, but you spent an hour to buy that time, if that makes sense. Exercise has a lot of other positives, though. It gives you a higher quality of life. You're less likely to become obese. You're less likely to develop Alzheimer's. And so I encourage you to exercise, but it's not necessarily going to make you live longer. Regardless, path analysis is low in internal validity, which means our ability to make causal statements, because it's based on correlational research. Another thing that you can do is what's called a cross-lagged panel design. What this would do is this would be measuring people at two different points, say 10 years apart, and see if correlations still hold. So you might be looking at something like extroversion and how it's correlated to drinking and smoking, and then you might measure people at 25 and 45 and see if that correlation is still present, and then that would allow you to theoretically make some sort of causal statement. And just as one other aside, the big five personality characteristics, extroversion's one of those, are thought to be stable across the lifetime. What is ex post facto research? Well, I'm getting deja vu here, because we've already talked about this. Things like gender, handedness, alcoholism are all studied after the fact. A non-equivalent groups design. This compares effects of treatments on pre-existing groups of people. So an example of this could be, you could look at social class and educational outcomes. All children go to school, but they start from different places. Again, this is not an experiment. You can't make causal statements, but it's not something you can manipulate either. You can't put kids into different social classes. They start out that way. Okay, let's talk about longitudinal and cross-sectional designs. Longitudinal analysis is where you study the same group of people, often for years at a time. I'm interested in gerontology, and this is a controversial area. People talk about what's called successful aging. These are studies to try to determine who lives the longest and what qualities they have and what you can do to live longer. It's criticized, though, because what about people who die? Were they unsuccessful in their aging? And so it's an issue. In cross-sectional studies, you examine different people at different points in their life at the same time. And so think of it this way. You could study attitude change. You could look at it specifically about marijuana legalization. And what you could do in a longitudinal study, you would follow people for years and see how their attitude about legalizing marijuana changes. If you did a cross-sectional study, you would grab a group of 20-year-olds, a group of 30-year-olds, 40, 50, 60, 70-year-olds, and you would say, when do people tend to change in their beliefs about marijuana legalization? Now, it's much easier to do a cross-sectional study than a longitudinal design, because you don't have to follow the same people for years and years. But you need more people in a cross-sectional study, and you have to use even weaker statistics than you would use in a longitudinal study. So There's no magic bullet here. A pre-test, post-test design, you measure behavior before and after an event. So this allows you to see if an intervention worked. So some people take ACT prep classes or GRE prep classes. Well, you get a practice effect from that, and that makes you more familiar and relaxed with the testing in general. And so there's no control condition here, as it says on this slide. And I guess, like I said, too, you get practice effects, also called pretest sensitization, which would definitely be jargon. A way around this is what's called a Solomon four-group design. Now this gets complicated, but it's the last thing we're going to talk about. So one group gets everything, the pretest, the treatment, and the post-test. Another group gets only the pretest and post-test. And then a third group gets the treatment and the post-test, and a fourth group only gets the post-test. Here's the thing. If you're going to go through all that work, just do an experiment. So the Solomon four-group design is really overcomplicated, I guess is what I would say. And that wraps up Chapter 5, and thank you for listening.